Convection and weather. Weather is essentially the atmospheric conditions that we experience on a day-to-day basis, the temperature of the air, the movement of the air, and the moisture content of the air. And it's predicated on a concept called convection. So let's focus on that first. So convection has to do with the uneven heating of the Earth's surface. So light from the sun is, at least the visible component of it, is able to flow through the atmosphere unimpeded. And when it reaches the ground, it interacts with the ground, and some of that energy gets reflected back into space, but some of it ends up being absorbed by the ground. And remember, the first law of thermodynamics says we cannot create or destroy energy. So if we lose energy in the form of light, it has to get converted to something else. And what it gets converted to is thermal energy, heat. So what we see is sunlight hits the ground, and the ground is going to get hot as a consequence of that. So light energy is lost, and an equivalent amount of heat energy is gained. Now, when the ground gets warm, what happens is it conducts some of its heat to the atoms immediately above it. So it transfers some of its thermal energy to the air that's directly in contact with the molecules along the ground. Now, as air becomes hot, what happens? Well, if you recall, when atoms are moving slowly, they snuggle in close to each other, so the density of a material is high. But as atoms move faster and faster and faster because they're getting hot, they bounce off each other, and there's empty space between these atoms. And what that does is that makes the density of the material lower. So hot air, just like hot anything, has a lower density than cold air. So we find is this hot air, because it is less dense, begins to flow upwards. And we call that upward movement of heated materials in a gravitational field, what heated fluids that is, we call that convection. So just as a styrofoam or beach ball will float to the top of a pool because it's less dense than the water material, this hot air will float upwards because it's less dense than the air around it, like a hot air balloon. It's the same reason. It's less dense. Now, as things go up, remember, in the troposphere, as we move upwards, the temperature drops. So what happens is, as the air is moving upwards, it's cooling off, but now it's got some momentum, so it's going to continue to travel upwards, but it's going to get colder. And as it gets cold, it's going to be colder than the air around it, and now it's going to sink downwards. And so we get this circular movement of air, and we call this circular movement of air a convection current. So or a convection cell. So this is a pretty good diagram that displays this. So the idea is radiation from the sun hits the ground, warms the ground through radiation. The now heated ground material conducts heat to the air. The air becomes less dense and rises. And that movement is called convection. Now, as it goes up, remember, the temperature is going to drop. And this is a big takeaway. As air moves up, the temperature drops. When the temperature drops, what happens is the ability of the air to hold moisture goes down. So when you cool air off, it causes clouds to form. Clouds form because the temperature drops and the moisture, the water molecules in the air begin to stick together, forming droplets, which we call a cloud. And as these droplets get bigger, we get precipitation. So we associate the upward movement of air with the formation of clouds and precipitation. Oh, by the way, this also shows something that will become important when we talk about hurricanes, which is that as these droplets form, they release heat energy. So if you recall from chemistry class, there was a concept called heat of vaporization. It takes a lot of energy to cause water molecules to separate from each other and evaporate. Well, when those water molecules come back together from a gas or vapor back into a liquid state, they release that same amount of energy. Again, because the first law of thermodynamics says we can't create or destroy energy. So however much energy it took to separate water molecules, you get it back when they fall back together as a liquid. Now, so the circular movement that we get is called a convection current or convection cell. And they happen all over the planet. Now, the main thing is that we need to start to associate this with a phenomenon that you and I call wind. So let's look at the classic example of a beach. If you go to the beach, it's always windy at the beach. And there's a reason why. There's always convection at a beach. Why? Convection is caused by uneven heating. And what happens is water has a very high specific heat capacity, meaning you add the same amount of solar energy to water that you do to land, the water doesn't change its temperature as much. It has a higher specific heat capacity. It takes more joules per gram to heat up water than it does dry land. So what happens is the land, with the same amount of sunshine on it, gets hotter than the sea does. So I have hot air here. It's going to rise upward because it's less dense. As it does, it's going to get cold, it's going to sink back down. And so it end up getting this circular motion called a convection current. Well, now, if the air is moving, that's what we call wind. So you notice this boat is tipped this way because the wind is blowing off the sea towards the shore. All right, we call this a sea breeze because it's coming off the sea. So during the day, we get this sea breeze caused by the circular movement of air. Now, as the evening comes on, what we find is that now the land and the sea are at the same temperature. The wind stops, which as a surfer, that's the best time I got because the waves are glassy. But then at night, what happens is the land is able to cool off more than the water is, again, because it has a lower heat capacity. So as it radiates energy into space, it changes its temperature more than the water does. So now the water is warmer than the land. So now we get what's called a land breeze. So what happens is the warm air is now rising off the ocean and sinking on the land. And now the wind is blowing in the opposite direction. So the big takeaway here is wind is just convection currents, and convection currents are caused by uneven heating of the Earth's surface, which causes hot air to rise and cold air to sink. But it's very important to keep in mind that as we move up in the air, temperature drops at a pretty constant rate. It depends a little bit on the moisture content of the air, but generally speaking, we can say that there's a drop of about 7 degrees Celsius for every kilometer of altitude you go up. So you go up 2 kilometers, it's going to be 14 degrees colder. You go up 10 kilometers, towards the top of the troposphere, you could expect the temperature to drop by about 70 degrees. So it's quite cold up near the top of the troposphere. And because the temperature is dropping, water cannot stay in a vapor state. It's going to condense into a cloud. So again, very important idea here. Rising air equals clouds and rains, because as you move that air up, the moisture it's carrying, the evaporated water it's carrying, is going to condense as the temperature drops, and those drops will get big enough to cause precipitation. So this is sort of one of the main concepts in this atmospheric unit. Rising air equals clouds and precipitation. So here's just a graphic showing it back to our ocean land. So during the day, since the hot air is rising over the land, I expect clouds to form over the land and maybe even rain. At night, the opposite happens. Now the water is warmer, so I expect clouds to form out over the water rather than on the land. And this is a very easily observable phenomenon. So the troposphere is where all convection occurs. So no matter how much convection we get, it can't move air above that. So basically, the troposphere is basically the limit of it is set essentially by the ability of convection to raise to send air molecules heading upwards. Now let's look here. I take warm air and I lift it out of this region because it's less dense. If I take molecules away from an area, the air pressure is going to go down. So I would always say to students, think about a car. If I let air molecules out of a car tire, the pressure in that car tire is going to go down. If I take air molecules that are at the surface and take them away from this area, there's fewer molecules here, the pressure is going to go down. Now, these go up, they flow across, and now they sink downwards. Now I have this region of Earth's surface here, this air near the Earth's surface, and I'm adding molecules to it. Well, if I add molecules to it, the pressure is going to go up. Think about a car tire. If I want to increase the pressure of a car tire, I push air molecules into the car tire with an air pump. So as I add air molecules, I pump air molecules in this region, I shouldn't be surprised if the pressure gets high. Now there is a very simple, easy to remember phenomenon, which is everything flows from high to lows. So it's true for water flowing downhill. It flows from high ground to low ground. It's true of voltage. Electricity flows from high voltage to low voltage. And fluids, whether it be liquids or in this case gases, they're going to flow from regions of high pressure to regions of low pressure. The pressure is high here. The pressure is low here. So things are going to flow from high to low. That's where the breeze is going to move. All right. I guess I already said that. All right, now thunderclouds are good examples, a good way of visualizing the troposphere and convection. What happens is you have very rapid convection happening here, and these clouds go all the way up. When you see this anvil, that's at the tropopause. It's basically 10 kilometers up. These things basically represent the entire height of the troposphere. And what happens is, as air rises up, the latent heat is released. These droplets, as they form, as the gas goes back to a liquid state, it adds heat energy to the cloud, causing convection to even increase. And so we get these huge, huge clouds. Um, yeah. Okay. So that's pretty much it for convection. I mean, there's more we could say, but that's as far as we're going to take it here. So now let's talk about this phenomena here. So remember, as air moves upwards, it gets cold. And as air gets cold, it loses its ability to keep water in a vapor state. And so the water condenses and then precipitates. So anytime air is moving upwards, we should be thinking clouds and precipitation. And with convection, what's the reason it's moving upward is just less dense, is heating and moving up. But there's another reason why it could happen, and that comes into play in the concept of a rain shadow. What happens is, if you have mountains that are basically, usually they're going to find them near the ocean, but they don't have to be. If the prevailing winds are such that they tend to push the air up a mountainside, as air moves up a mountainside, it gets cold. The top of the mountain is colder. So as this air moves up, it gets cold, and then it forms clouds and precipitation, and it rains on one side of the mountain. But then when it comes down the other side of the mountain, the moisture's all been drained out of it by the rain on one side. So we get dry air on the other side, and we call that dry zone, where often we'll get deserts. We call that a rain shadow. So in regions where there are strong prevailing winds, especially if they're near the ocean and carrying a lot of moisture, what we find is the windward side, the side that's closer to where the winds are blowing, uh, tends to have rainforests, or if not rainforests, then very thick, deciduous forests. And then what we find is on the other side, where it's already lost its moisture, we tend to get deserts. So you can find this very close together. So in the state that I'm from, Washington State, and the nearby Oregon State, we see this phenomenon quite a bit. So here's the Pacific Ocean. If this is Washington State, there is a set of mountains called the Cascade Mountains. And as this air is pushed upwards by the prevailing winds, are pushing this moist air. And why is it moist? Because it's got all this evaporative, it has all this water vapor picked up off the ocean through evaporation. As that air gets pushed into the mountains, it gets pushed upwards because the air is flowing this way. So it's going to move up. Well, as it moves up, what happens is it gets colder, and as it gets cold, clouds and rain forms, but they form on this side of the mountains. Now, this is different from convection because it's being pushed just by being a prevailing wind. So it's not local convection that's causing it to happen. But what happens now is it loses all this moisture on the way up. So when the prevailing winds are still in the same direction. So when it comes down the other side, it's already lost its moisture. So now I have all this dry air. So I end up with this desert area, or if not a desert, an almost desert area. And we call that a rain shadow. So you'll see mountains where one side is heavily forested, often rainforest, and the other side is very dry, even desert. So here's a classic example from the state nearby me. I come from Washington State. This is Oregon State. My brother lives like right over here. And so what we find is this. We have the Cascade Mountains here, and I see all this forested land here and all this desert over here. And the reason that happens is, as winds come off the Pacific Ocean, they start to rise up over these mountains here. As they rise up, the air gets colder. The water that is carrying condenses and then falls out as precipitation, as rain or snow. So we get these very lush, rainy areas here. And then as it comes down the other side, it's now had all the moisture drained out of it by this upward movement. And so now I have dry air flowing here. So this is what a rain shadow looks like over here. We call this dry area on the what's known as the leeward side of a mountain range, a rain shadow. So when I look at this, I can tell when I see this sort of pattern of heavy forest with mountains that have heavy forest on one side and desert on the other, I'm thinking rain shadow. And I can tell that the prevailing wind must be from this direction, because that's why I have all this moisture falling on this side and not on this side. So you can tell prevailing wind patterns by looking at the distribution of vegetation. Now, weather, as I said earlier, it's basically the day-to-day atmospheric conditions. So we're talking about air pressure, wind, precipitation, temperature, and so on. And this changes from day to day. So there's, it can be fairly unpredictable. I mean, we can predict the weather for a few days out, but beyond that, we lose our ability to do that. Now, climate is something different. Climate is the long-term averages of weather. So although I may not be able to tell you whether it's going to be raining or dry 3 weeks from now, what the temperature is going to be, I can tell you that November in Korea is going to have a certain temperature and a certain amount of rain on average. That's called climate. And so climate is something that is not that volatile. It doesn't change that much, unlike weather, those changes day to day. Now, water has a profound influence on the climate and the weather in a particular area. So basically, what it comes down to is this: water has a high specific heat capacity. It's hard to make water warm, and it's hard to take warm water and make it cool down. It doesn't like to change its temperature. So if there's water, the temperature doesn't change very easily. If there isn't water, say a desert or some inland area away from the ocean, then we expect the temperature to be able to change quite a lot. Okay, so basically, we can think of this in two ways. We can think of proximity to the ocean where there's a lot of water, or we can think desert where there just isn't any water. Now, this is true even if we just compare areas near a body of water and not near a body of water. So let's just think first in terms of deserts. Deserts are notorious for having these very large temperature swings. It's very hot during the day, very cold at night. That's why, because there isn't much moisture there. So there's not a high heat capacity, so it's easy to make it hot when the sun shines on it, and it's easy to cool off when the sun doesn't shine on it. Now, coastal areas are sort of the opposite of that. Because they have this big body of water, it doesn't heat up. So the sun shines down, but this body of water keeps the air kind of cold, so it doesn't get really hot when the sun shines. Now, at night, it's not able to cool down much because, again, you got this body of water stays at a certain temperature. So what we find is the presence of water basically dampens the day to day and season to season change in temperature. So if you have lots of water, you have very little temperature change, both day and night and season to season. And if you don't have water, you have a big temperature change, both day to day, or day to night, and season to season. So let's just look at a couple examples. We'll compare London to Winnipeg. So neither one of these is a desert, but London is on the water, and Winnipeg is landlocked. It's inland. They're at the same latitude, though. So if you notice, from summer to winter, if you compare the average temperatures in summer and winter, what we find is London has a temperature divergence between summer and winter of about 24 degrees. Winnipeg, on the other hand, it's more like 65 degrees. It's a considerably larger change, and that's because Winnipeg is not near the ocean, so it doesn't have that big body of very high specific heat capacity water to modify those temperature changes. Similarly, if we just look at the day-night temperature changes, we'll notice that we get bigger day-night temperature changes here than you do here. Now, it's not as immediately obvious from this graph, but if we average these day-night temperatures across these values that they give us, what we'll see is these values are smaller than these values. Here, let's take a look. So what we see is in London, the day-night temperature average, if I take all these values and find the difference and average them, I'll find it's about 11 degrees. Whereas in Winnipeg, the difference is about 17 degrees. If I was to choose a desert, it would be even more than that. Okay, so that was a long one. Sorry about that, but thanks for watching.